Good afternoon, students. So today's topic is effective water table on bearing capacity of soil. Okay. So the bearing capacity equation, which is derived by Terzaghi, is based on an assumption that the water table is located well below the foundation. That is, water table is not affecting the foundation. So in that equation, there is no effective water table. So in practical situation, there will be water table and it may be at ground level or at footing level or between ground level and footing level, etc. Okay, so we have to consider the effect of water table also in practically. So next, so we can look through the effect of water table on bearing capacity. Okay, so in the previous equation, that is the general equation of bearing capacity is QU is equal to, for square footing it is QU is equal to 1.3 CNC plus QNQ plus 0.4 gamma B and gamma. So here there is three component. So first is cohesion component, and this is a surcharge component, and it is unit weight component. Okay, so in this equation, in the first equation, that is in the first term, C is constant and NC is constant. So the effect of water table will not affect the first term, because first term is constant. So in the next second term, it is Q and Q. Q means gamma df, that is unit weight into depth of footing. Okay, that is Q is equal to gamma df. So unit weight will vary based on water table. This, if the soil is below the water table, the soil will be in submerged condition. So unit weight will be submerged unit weight, gamma dash. Okay, so like that, second term will be affected by water table. Okay, and in the third term, here it is gamma, that is unit weight. So this unit weight also will vary with the effect of water table. So this third term also vary based on the effect of water table. So generally in this equation, in the Terzaghi's bearing capacity equation, the second term and third term is affected by water table. First term is not changing whether there is water table or water table is there or not. Okay, so note that point. First component is cohesion component, it is constant, so it is not affected by water table. Second component is surcharge component, and it is affected by water table because Q is equal to gamma df. And the third term, there is gamma, third term is unit weight component, is also affected by water table. Okay, so we can check the effect of water table. The terms affected by water table are soil weight component and surcharge component. That is, the second term and third term is affected by water table. So look through this figure. In this figure, this footing, and depth of footing is the distance from ground level up to footing base. Okay, so this is depth of footing. Okay, so surcharge component, that is second term is surcharge component, that is Q and Q. So actually this is the component by the soil which is for a depth up to this, that is df depth. So this is the surcharge component. Okay, and the last component, that is 0.5 gamma B and gamma or 0.4 gamma B and gamma, that is the last term, that is the third term, is affected by the soil up to depth B, up to the width of footing. Okay, that is the B comes here because the effect of the load will be for a width, for a depth which is equal to width of footing. That is, the pressure bulb will be for a depth which is equal to width of footing B. Okay, so below this depth B, the effect will not be there. So we have to consider the effect of stress up to depth B below the footing base. Okay, so remember, this is the surcharge component, this is the second term and this is the third term. Okay, so first case, so we can discuss the effect of water table at different levels. So in the case 1, we are assuming the water table at B below the footing base. That is, water table is at a depth B below footing base. So here it is the position of water table. Okay, so in that case there will not be effect of water table because it is far below the footing. That is, below the depth B there will not be effect of the stress. So since the water table is B below the footing base, in the second term and third term, gamma will be gamma bulk itself. There is no change of unit weight. So there is no change in the equation of bearing capacity if the water table is at B below the footing base. Okay, so if the water table is here or any distance below this point, there will not be effect. Okay, but if the water table is somewhere within this depth, there will be effect. Okay, so we can look that effect, that is in case 2, water table is at footing base. So this is footing base. So here water table is at this footing base, that is this is the location of our water table. Okay, so I have told that this is the second term of the equation and this is the third term. So since water table is here, this third term will be submerged condition, that is unit weight in the third term will be submerged, because here it is water table. So the soil below this water table will be submerged, submerged unit weight of the soil. So gamma in the third term will be gamma dash. Okay, and in the second term means the soil for this depth. Okay, so here the gamma unit weight of the soil in second term will be equal to gamma bulk, that is gamma itself, because water table is below this point. Okay, so this is the effect of water table if the water table is at footing base. Okay, so the equation will become, that is QU is equal to CNC plus QNQ plus 0.5 gamma dash Bn gamma, because in third term only gamma changed as gamma dash, because water table is at footing base. Okay, so in problem, if there is any location of water table, you just draw the rough sketch of the footing and mark the water table where it is located, and then change the unit weight component as gamma or gamma dash. Okay, that is the procedure. So this is the second case, that is water table is at footing base. Next, in third case, water table is at ground level. Okay, that is here, this is the location of water table. So what will happen if the water table is at ground level? The second term and third term will be in submerged condition, because the water table is above these two components. So gamma in second and third term is gamma dash, that is submerged condition. Okay, so these three cases are very simple, because here it is at a depth B below the footing base, and here it is at the footing base, and here is at the ground level. So these are the three levels, that is B below the footing base, this is one level, and this is the another level, and this is the last level, ground level. So in these cases, if there is any water table, that is if the water table is at a footing base or at ground level, you change the unit weight like that. That is, if the water table is at ground level, the whole component will be in submerged condition. So in the second term and also in third term, the unit weight will be submerged unit weight gamma dash. Okay, and if water table is at a footing base, the unit weight in the third term will be gamma dash, and in second term will be gamma itself. Okay, that is the case. And next two cases are if the water table is in between ground level and footing base, that is if the water table is within this depth, somewhere between ground level and footing base, that is one case. And another case, if the water table is between footing base and B below the footing base, that is somewhere between this depth. That is another two cases. Okay, so first we can discuss the water table is at between ground level and footing base. So let us assume the water table is at a depth dW from the ground level. So this is water table, and the depth of water table from ground level is marked as dW. Okay, and dF is the depth of footing, that is the distance between ground level and footing base, dF. Okay, so for deriving the effect of water table, we can write the unit weight in second term, that is this is the second component of second term. So since water table is here, the third term will be submerged unit weight itself, because water table is here. Third term means the soil which is at this location. So in the third term component, unit weight will be submerged unit weight gamma dash. But in second term, the full soil is not in submerged condition, that is the soil for this depth is only in submerged condition, and the depth for the depth dW it will be in bulk unit weight. So we have to generalize this equation. Okay, so we can write gamma in second term is equal to gamma into dW. So for this depth dW it will be in bulk unit weight, because water table is below this point. Okay, that is gamma into dW. Next, for this depth, so this depth is df minus dw. So that is the depth from this point to this point, that is df minus dw. So for this depth, the unit weight will be submerged unit weight, since water table is above this point. Okay, so gamma dash into df minus dw. And by rearranging this, we will get the equation like this, that is you take the component of df and dw together, that is gamma dash into df plus dw component means gamma minus gamma dash into dw. Okay, then we can approximate gamma dash submerged unit weight as bulk unit weight by 2. Okay, that is unit weight of water is 9.8 kilonewton per meter square, and bulk unit weight is 19 or 18 kilonewton per meter cube. So approximately submerged unit weight is equal to half the bulk unit weight. So we can approximate it as gamma by 2. Okay, so by rearranging, we will get gamma into df into 0.5 into 1 plus dw by df. So this is the equation of the second term if the water table is in between. Okay, that is gamma in second term means second term will become gamma df into this factor rq, and this is replaced by a constant, that is rq. Okay, that is in second term become gamma df into this component, that is rq. That is the change in second term if the water table is between ground level and footing base. And gamma in third term will be submerged unit weight itself, because water table is here. So the third term, the soil in the third component, that is the soil for this depth, will be submerged condition. So in third term, this gamma dash itself. Okay, that is in second term there is a introduction of constant rq, and its value is 0.5 into 1 plus dw by df. Okay, and we can discuss the fourth case, that is if the water table is between this depth, that is between footing base and width b. Okay, so mark the depth of water table from footing base as dw dash. Then write gamma in third term. So here it will be this is the component of soil that is in third term of bearing capacity equation, and in the second term is the soil here. So here it will be in bulk here the unit weight of soil will be bulk unit weight. So gamma in second term is gamma bulk itself. So there is change of component or change of the term in third term. So we can derive that equation. This in third term dw dash into gamma. For the dw dash depth, unit weight is bulk unit weight, because water table is below this point. So gamma into dw dash plus this gamma dash for a depth of b minus dw dash. This is b minus dw dash into gamma dash. And in the as in the previous one, you rearrange by taking b term and dw dash term. Okay, and replace gamma minus gamma dash as gamma by 2, and it will become gamma b into 0.5 into 1 plus dw dash by b. That is in the third term there is an introduction of another parameter, and is replaced as a constant r gamma, and its value is 0.5 into 1 plus dw dash by b. Okay, so here also in the third component this new parameter came, and here in the second component this parameter rq came. It is replaced by rq and it is r gamma. So in general we can summarize this into a single equation. Okay, that is in short qu is equal to cnc plus qnq into rq plus 0.5 gamma b n gamma into r gamma, where rq is equal to 0.5 into 1 plus dw by df, and r gamma is 0.5 into 1 plus dw dash by b. So this is the equation of bearing capacity if there is any water table in between footing base and ground level, or in between footing base and width of footing b. Okay, so remember in that case there is an introduction of two constants rq and r gamma in second and third term respectively. That is in second term there is a constant rq, and in third term there is a constant r gamma, and this rq and r gamma is known as correction factor for water table. and its value is RQ is equal to 0.5 into 1 plus dW by dF, where dW is the depth of water table from ground level, that is dW, and R gamma is 0.5 into 1 plus dW dash by B, where dW dash is depth of water table from footing base, dW dash. Okay, so remember this dW and dW dash, that is dW dash is the depth of water table from footing base and dW is the depth of water table from ground level. Okay, so in short, if the water table is in between any two level, that is in between ground level and footing base, and in between footing base and width B, you remember this equation only, that is CNC plus QNQ into RQ plus 0.5 gamma B N gamma into R gamma, where RQ is 0.5 into 1 plus dW by dF and R gamma is 0.5 into 1 plus dW dash by B. Okay, so this is this is RQ is in second term. Okay, RQ is the constant for second term, and for second term means the water table in between ground level and footing base, that is the second term, that is surcharge component. So it will be dW is the depth of water table from ground level, that is dW by depth of footing dF, and R gamma is constant in the third term. Third term means unit weight component. So here dW dash is the depth of water table from footing base and B is the width of footing. Okay, so this is the correction factor for water table, and this RQ and R gamma, the values of RQ and R gamma varies from 0.5 to 1, that is its minimum value is 0.5 and its maximum value is 1. Okay, so in problem, if you get the value of RQ and R gamma less than 0.5, so if for example if you get the value as 0.3, you have to approximate it as 0.5, that is minimum value is 0.5 and maximum is 1. For example, in problem, if you have get the value of RQ and R gamma as 1.3 etc., if it is 1.3, you have to approximate as 1 because maximum value is 1. So remember this also, that is RQ and R gamma ranges from 0.5 to 1, minimum value is 0.5 and maximum value is 1. Okay, so this is the effective water table in bearing capacity. So this is the equation. Okay, so you by heart this equation and this RQ and R gamma. And if the water table is at ground level and at footing base etc., that is in case 1, case 2 and case 3, you need not so in these cases, that is for case 1, case 2 and case 3, you need not by heart that equation. In that cases, you change gamma as gamma dash by drawing this figure, that is if water table is at ground level, at footing base or etc., like that you change the unit weight, that is if water table is above the soil, it will be in submerged condition, and if water table is below that soil, the soil will be in bulk condition. You remember that only. Okay, so if the water table is in between these points, that is in between this depth or in between this depth, you by heart this equation and by heart this equation, that is the correction factors for water table. Okay, so this is the effect of water table on bearing capacity. So we can do some problem. So I will put the problem in the next video. Okay, thank you.